Okay, welcome back. We're going to do part two of drilling and tapping a blind hole. So in part one, we uh, drilled a center, we drilled the material with a center drilling hole and we calculated the spindle speed, the feed rate, the material removal time, the material removal rate, and the power requirement. So in this video, we are going to find all of those parameters for the twist drill and the tap parameters as well. Okay, so similarly to the center drill, the twist drill uh, spindle speed in RPM has a very similar, has the same formula. So start with N, which is equal to 12 V pi D. So at this point we know V, which we found earlier in the previous video, to be 100 feet per minute. But we don't know D. And so to find D, the diameter of the hole that you have to drill before you tap, you need to go to actually the tap table to figure out the diameter of the drilled hole. And it depends on the type of threads. So we are cutting half inch by 20 threaded hole. Sorry, this is distracting me. That shouldn't be there. So sorry. Okay, so we're going to go to the tap table, which is down here. We found that it is, we're doing the half inch by 20. So that's a fine threaded tapped hole. It has 20 threads per inch. And it says that we're supposed to use a 29/64 drill. So you can kind of compare that to a coarse threaded half-inch threaded hole, which would have 13 threads per inch. And you would use actually a different drill, a smaller drill, to drill that hole. So now that we know the drill size, we're going to go to the drill chart. And so here we have it. So we're going to look for the 29/64 drill. And we found it right here. All right. So this is the size of hole that we're going to drill. But there's a lot of decimal places that I really just don't want to carry at this point, because the accuracy of these drills can't possibly be to the 6th decimal place. That's just not. If you're going to use an accurate tool, a drill is not going to be the tool to do it. So these decimals come because a fraction just creates lots and lots and lots of digits. Whereas you'll notice a Z only has 3, a millimeter, maybe because of the conversion it has 4. But if you choose 3 decimal places, that would be a safe bet. You could use a reamer or bore the hole if you want a more accurate hole. So anyway, we're just going to use 0.543. So I'll switch back to the white pen here. And so now this isn't a question mark. Nope. There we go. It's now 0.543. And make sure that you get this right because I'm pretty sure it's 0.453. Yes, it's 0.453. My mistake. So I'll just move the page down so we have somewhere to work. So 0.453 inches. Okay, so we'll plug this into the calculation now. So n equals 12 times 100 divided by pi times 0.453, and that equals 12 times 100 divided by pi divided by 0.453. So 843 RPM. Yeah, so this is quite a bit smaller value than the center drill. The center drill had a 0.109 inch diameter cutting tool, and I think it was around 3,500 that the RPM was set at. And really, as this number gets bigger, n will become smaller. And that's sort of the relationship there. And as you go with a softer speed, maybe I'll use a different color here altogether. As you have a softer material where V goes up, N will go up. So you can kind of see the relationship here with the diameter and the surface speed. So hard materials, the N would go down because your surface speed would go down. Okay, let's switch back to white. Okay, so now that we have we found our RPM, our spindle speed, we'll put a box around it. It's always a nice thing to do for your teachers to find your final answers. So we're going to find our feed rate now. So F again equals N times FR. So we know this, but we don't know our FR. Our FR is not the same as our center drill. And so why is that? And it's because our recommended feed rate has changed now. So we're between a quarter inch and a half inch at 0.453, certainly. And so we're closer to the half inch. So we would choose a number closer to the 0.008. So this is just a rough guess, and I'm going to say that the number is about 0.007. So you may wonder why I'm a little bit loose with the numbers here, like dropping digits that were here, choosing not calculating the recommended feed rate. And you can really kind of, like what gives us a clue is that, and maybe this doesn't show what's going on here, but really, if you look at other tables, there's lots and lots of tables for materials and speed, surface speed, that they'll give a range, so maybe 200 to 400 for high-speed steel. Cutting tools, all of these would be numbers in between. This table, for simplicity, has just chosen the average of the range. So, um, and then these are kind of, loose altogether as well, giving a range. So we're just going to make a rough guess that this is 0.007 inches per revolution. And in reality, you would try these out. You would, see how your material reacts when you're machining and adjust from there and fine tune when you're actually machining. This just gets us in the ballpark. Okay, so going back to, just going to change my pen color again. So this equals 843 RPM times 0.007 inches per revolution. So the revolutions cancel, and you're left with inches per minute for your units. So let's just calculate this now. So we have 843 times 0.007. And we get 5.901. So I'm just going to use 5.9. Inch per minute. Okay. So now that we know our feed rate, we can figure out that was item 2. This is item 1. Our item 3, which is our material removal time, MRT. So that's L plus A over F. Now for the center drill, we were just trying to put a little spot that this drill that we're calculating can follow. So this was just roughly put in at 0.1 inches. L plus A equals 0.1. But we actually need to figure out how far we're drilling. Okay. So just going to drill the hole here. So it said that our threads needed to be, well, I can't remember. Let's go back to the question here. So our threads needed to be 0.6. That's where the inches should be. Oh, this just riddled with issues. All right, forgive me. So machine to 0.6 inches deep. Okay, so the threads need to be to 0.6. But let's say we always need to leave a little bit of space here so that the tap can go into the hole and not bottom out into this chisel area. And this is A. And you could calculate the angle here and do some trigonometry to figure out, well, this isn't a very good triangle. The triangle would be more about there. It's bugging me now, so just get rid of that there. So you could do trigonometry and figure out, you have half your diameter would be there, and you have an angle, and depending on the drill you're using, they have different angles. But really, we just probably don't want to break through the material if it's a blind hole. And we're definitely not going to do that since it's 0.6 and this is, um, 1 inches. So we're okay there. Um, but you could figure out that with your d over 2 and the angle of your drill, you could figure out this height here and be more precise. But a, we're just going to assume is a is equal to d over 2, and that's just a base of an assumption. And then for b, I'm going to call it in this video. I don't know what it's actually called. I'll switch my pen here to maybe, let's try blue. So B for blue. Okay, so B is 3 thread pitches. So thread pitches, 3 times your thread pitch. So again, we're going to go back to the question. And there are 20 threads per inches, and I see that right there. So the hole depth, which is going to be this entire top number, is going to be, I'm just going to switch back to white. Oh, that's a big pen. Okay, let's just fix that there. Okay, so MRT is going to equal the length, which is definitely 0.6 because we need 0.6 inch threaded hole, plus 3 times 1 over 20. So 3/20ths of an inch is going to be this B. So maybe I'll just clarify that. So thread pitch is 1 over threads per inch. So it's just the inverse number. And then we're going to add the diameter over 2, which is 0.453 over 2. And then that's all going to be over our feed rate. So I make mistakes when we do math, so I'm just going to calculate the top first. So 0.6 plus 3 divided by 20 plus 0.453. Oh, 53 divided by 2. Okay, so the top is 0.9765, and our feed rate was 5.9. So this is probably going to go in a bit slower than the center drill. And it's going deeper, so it's obviously going to take more time. So let's just calculate this. So 5.9, so we'll divide this by 5.9. And that equals 0.16. It disappears every time. 166. Okay. Minutes. So how many seconds is that? Again, I'm a seconds guy when it comes to decimal minutes. So we'll times that by 60. And that's about 10 seconds. Okay, so now that we have our MRT, we can figure out our material removal rate. So MRR is equal to, well, you can calculate it two ways. I'll show you a different way here. So if this is our time, we can just figure out our material removal. Never mind. Let's just do it the old-fashioned way. So pi t squared over f over 4. You can review the notes and it goes through how this comes down to this formula. There's a bit of simplification in it, so I just wanted to avoid that. Anyway, so move the screen down. So this is pi. Now the diameter is 0.453. We're going to square it. Our feed rate is 5.9, and we'll divide this by 4. Okay, so plug this back in. So pi times 0.453 squared times 5.9 divided by 4 is equal to 0.95. .95 inches cubed per minute. And if you want to get technical, I guess 0.951 inches cubed per minute. Okay, so we can now that we know that, put it in a box, and we'll use that number to calculate our power. So power again equals our unit power times our material removal rate. And again, we'll just use, it's the same material, so we're going to use, we looked up earlier that it was about 130 Brinell hardness. This is kind of off the scale here. So we're just going to go with 0.6. So this equals 0.6 times 0.951. And that is equal to 0.57 horsepower. Okay. And I think I made a calculation error in the last video. I multiplied this by 750, but really I should have multiplied it by 745 or 746. So I have a way of remembering that, and there's 745 watts per horsepower, and I'll remember that because that's the area code of, or not the area code, but the 204.745 2944 was my home address when I grew up. Well, that one's supposed to be brackets, but anyway. So I'll remember that now. You can call that number. Nobody. I think that number's been discontinued now, so you won't get anybody there. Anyway, now this has some real juice here. So before, I think we were all getting low numbers, like in the 30 watt range, but 0.75 times 745 is equal to 425 watts. So that's nothing to sneeze at. Um, it was kind of an off-colored joke, I guess, during these times. But that's if you think about a lawnmower, some lawnmowers are about a quarter horsepower, things like that. So this is about a half horsepower, which puts us into the 425 watt range. So that's not bad. That's you're going to start to need to step up the motor in the CNC mill that you're designing, possibly. Maybe that'll be a job that you get one day, designing the motor that needs to go into a CNC mill. But anyway, and that's why really you need to calculate how much power you need to drill a hole, is to design the CNC machine that you're going to be manufacturing so that your end user can manufacture their products. Okay, so the last item that we need to do is um, tap the hole and determine those parameters. So this is going to be the tapping portion of the video. So we're going to figure out the spindle speed, the feed rate, and the material removal time. Okay, so first we're going to figure out N. Now for tapping, the formula is exactly the same for your spindle speed. So N equals V, 12 times V over pi D. Now V changes. There are tapping parameters. So let's go to the tapping parameters here. You know what? I didn't copy it into this worksheet, so I'm gonna have to go find it. This isn't a bad segue into the document that I created for you to do all these calculations. So I've uploaded these, and you can see this material all on Learn as well. So let's just snip this into the workspace environment that I'm working in. Okay, so we're tapping into mild steel, so we have mild steel here. So again, this one's showing a range, so we could choose 30, we could choose 50, we could choose a middle point. But maybe for the first time that we tap this hole, let's just use the slower speed, and then if we find that it's going too slow in production, we could always ramp up to 50 surface feet per minute. So I'm going to choose 30 here. I'll switch to the red pen. I'm just going to circle where I got that from. Okay, so mild steel. And I need to switch to my pen function. There we go. Okay, so mild steel. And I'm going to use 30 surface feet per minute. So V is equal to 30 feet per minute. And that, if you compare that to the first one, it was 100 for drilling the hole. So it's quite a bit less, about a third. of the speed. Now the diameter as well, we need to choose the diameter from this tap table. So the basic effective diameter, so we're going to choose the largest diameter. And so not the basic major diameter, that's just something you would use to, I don't know, say it's a 1/2 inch tapped hole. So we're going to use 0.4675. So get a red pen and we'll also circle that. So there's a decimal there, 0.4675. And again, maybe we should just round that to 0.468. Change it back to white. So D is equal to 0.468 inches. Okay, so now that we have that, well, let's calculate the spindle speed. So 12 times 30 divided by pi times 0.468. And so when we calculate that, 12 times 30 divided by pi divided by 0.468, and that's now equal to 244, well, let's call it 245. Again, I have a little bit of flexibility here because this is 30 to 50, so if I had put 50 in there, we would have got a higher number. So I'm able to, round this number liberally. Maybe 250 would be okay as well, just staying under that 50 surface feet per minute. So we're going to do 245. RPM. Now our feed rate changes considerably because we need to match the feed rate. It changes considerably from drilling a hole. We need to match for a threaded or a tapped hole. We need to match the feed rate to the spindle speed. Otherwise, you could go in too quickly and break the tap, or you go in too slowly and strip out the threads or break the tap, whichever comes first. So the formula for a tapped hole is your feed rate is equal to N over your threads per inch. So we know that it's 20 threads per inch. So F is going to equal 245 divided by 20. And so that equals 245 divided by 20. That equals 12.25 inches per minute. Now, I'm going to keep all of these decimal places. And if this was 245.8 or 244.8, I would probably have more decimal places. And if I had more decimal places here, I'd have more decimal places here. But a CNC machine often can only, there is a limit to what you can program. And since this has to be perfectly divisible and keep all the decimal places, you need to choose, play around with this number here so that you don't exceed the decimal places of the CNC machines. So having 2 decimal places is probably sufficient, but this absolutely needs to go at this feed rate, 12.25 inches per minute. So no rounding here. No rounding, no truncating. Man, maybe I'll use another pen. Maybe I haven't used yellow, so maybe I should put a big balloon around this and say, this has gotta be, all of those decimal places. Anyway, I think I beat that horse till it was dead. So we're gonna keep going here. And now we're gonna find the time that it takes to tap this hole. So I expect probably less time than drilling the hole, but could be surprised. So MRT is equal to L over F. So we're only going to go down to 0.6 inches, so L is 0.6 and 12, and our feed rate is 12.25. So our material removal time is 0.05 minutes. Or 0.0, yeah, 0.05 minutes. And let's see what that is in seconds. That's about 3 seconds. Okay. So there you go. We've calculated the spindle speed, the feed rate, and the material removal time for tapping a hole. So you may ask yourself why I didn't calculate the material removal rate and the material and the power. And my sort of justification for that is that the threads are such a small portion of the material removed that there wouldn't be very many forces, and there isn't much material there, so I think it's quite negligible at this point. So that concludes this video for drilling and tapping a hole. We'll see you in the next video.